your very best to just chunk it out and pick a couple hours to study each day, and don't binge study or cram like on Monday or something like that. But you'll be able to watch the YouTube video a couple times. And something that I noticed is our old YouTube videos are still on there, and they're labeled the same. So you could still go to chapter 16, part 1 and 2 from last year, and it covers all this material again, and it'll probably be very similar to this, but also just maybe said in a different way or something like that. So if you get bored with this video or you're looking for another outlet, like give it a try. And all those videos from last year are still up, so you can always watch those. All right? So for today, with coordination chemistry and isomers and talking about color, there's a lot of material that I would say is like pseudo-memorization. There's parts of it that you have to have memorized or be familiar enough with so that you can solve problems, but that still means there's a conceptual nature about the problem that helps you focus the material you've memorized. So what I mean is, today is going to feel a little bit like being spoon-fed. Like there will be things and you'll be like, why are they saying that? Like, we know this. But that's just how it is. That's how this section is. It's a lot of just naming. And back to some of these basic things that you learned in Chem 105, but we're just throwing a twist on it. So if anything, in terms of math and hardcore number problems and things like that, that was last test. Titrations and acid-base chemistry. There's a lot of solving for pHs and pOHs and things like that. Here, it's more of a conceptual test, but it kind of feels like coordination chemistry in terms of what it talks about and what's covered is its own little island somewhere existing in the world of Chem 106. Like, it's hard to take what we learned last section and we've learned maybe this whole year and like mega apply it or just easily transition into this section. This section feels like it's quite a bit on its own. So, just take this section. If you're struggling with this section, just do enough practice problems and just get familiar with the jargon and how the problems are. So to start off, we just need to start off by looking at coordination spheres. And the most basic problem, and probably on there several times in your exam, is some type of naming situation. Whether you have to pick the correct name for a coordination sphere that's given to you, or you're given the name and have to pick the formula, okay? So first things first, again, some of this will seem basic, but we're going to run through it all. A coordination ion, right? A coordination sphere can produce an ion, but it is not just like a regular polyatomic ion. So when you see something like NO2 minus or NO3 minus like nitrate, right? We're used to seeing things like that, polyatomic ions. Coordination sphere chemistry is similar, but it's very different at the same time, meaning what goes on inside of these special brackets does not act like a salt or like regular ions would, right? Like in an ion, we would see potentially resonance structures and things like that, right? But with coordination chemistry, it's quite a bit different, and the structures look a little different. So our main focus in coordination chemistry is what's within the brackets. And the things that are within the brackets as a whole can be charged, right? Or are charged usually, whether they be a cation or an anion. And so it's up to you to use your chemistry knowledge and skills to look at what's inside the brackets and predict whether what will be the net positive charge or what will be the net negative charge depending on what is bonding. Now in coordination sphere chemistry, we always have what I would like to think of as the heart of a coordination sphere, and that is the metal ion, right? The metal atom. It's usually a transition metal. Not always. I'm pretty sure it always is. Okay? And for us, it's the cobalt here, right? The cobalt is the center of everything. It's the center of attention. And the rest of these inside of the brackets, we call them ligands. Okay? The ligands come in and they act as Lewis bases. So that is old news for us. Lewis acids and bases. But to go over that again, a Lewis base is something that will donate its lone pairs of electrons to a Lewis acid, which therefore accepts them, right? So our Lewis acid, in this case, is our cobalt ion, right? And all of the Lewis bases also the ligands for coordination sphere chemistry, are the pieces that are within the brackets. Now, it doesn't matter if the pieces within the brackets, they don't have to be ions by themselves. They don't have to have net charges. But they have to have lone pairs readily available to donate, right? If there are no lone pairs to donate, it's not really a ligand, okay? So we're getting down to some of the basics there. So in terms of ligands, right, they can take on basically any form. Anything can be a ligand as long as we have lone pairs and they're willing to bond to a metal center atom. So in this first case here, we have the ammonia, right? We have two of them and we're bonding. We also have this abbreviation EN, which you're familiar with now, ethylene diamine. Now, there are several different types of ligands, and we would call them polydentate ligands, which means that it's a ligand that's going to bond to the middle metal atom in two or more places, right? Polydentate, two or more places. If it's two places specifically, it's called bidentate. So, if you're given a problem to name or to write what the formula is of a coordination sphere, and they tell you that something is tridentate, then you know it has to bond in three places. And it's important to know those things because it's up to you to say whether or not something is valid and can occur or cannot occur. So that dentate is important. This one, ethylene diamine, we know, is bidentate, or bonds in two different places. So if we would have two of those, how many places on the cobalt does it take up? 4 places overall. So in questions where they ask you to say, what is the coordination number of the coordination sphere? It is the count of how many places on the center metal atom are being taken up, or how many bonds are being made from ligands, okay? So not how many ligands are there, because this one there's only 2, but they take up 4 places. But how many places they are. And that segues us perfectly into an important concept. Over here, there's a slide, and I think a lot of us brushed over it, but it's important. He wanted you to memorize this. Cobalt 3+, and chromium 3+, and this right here, they follow this much for their coordination number, always, right? It'll always be 6+ for this one, always. And it'll always, not 6+, sorry, 6 for just the coordination number, 6 for the coordination number, and 4. I don't know why that's required to be memorized. Beyond the fact that maybe he'll ask you to create one, or pick one that's valid, or pick one that's invalid, or something like that. But having this memorized is a must. So keep that in mind, okay? So when we look at this, number 1, anytime we would write salts before, like something like sodium chloride or potassium nitrate, the cation always we write first, right? You don't ever see something like this. ClNa. Right? We always write the cation first. So if immediately we see our brackets coming first in this whole ion here, then we know that our coordination sphere is a cation. Okay? And so in naming, and you guys have done a lot of practice with this, so I know this is pretty good review. And most of you are just watching me just shaking your heads, yeah, we know this. But we're going through it slowly. We would have to put what's in the sphere first because it is the cation. That's always how we name it. Okay? So when we are going to name the sphere, the first thing you should do is determine whether it is the cation or the anion. Now we know for problem number 1 it is the cation, so we're going to name it first. And then a common mistake is that students run right for what the heart of the coordination sphere is to write it. They say, okay, we've got our cobalt here, we're going to start with cobalt and then name the ligands. But how we do this is we name the ligands first, and then we name the center metal atom at the end, okay? So the ligands will come first. And we don't name the ligands according to how we've placed them inside the coordination sphere, but rather their specific names by themselves. So what is the name for ammonia in a coordination sphere? It is an amine, okay? And the EN, we've gone over, ethylene diamine. So it's absolutely crucial that you are familiar with those things. So what does that mean for you? Memorizing that box that goes over the ligands that we've gone over in class and on the slides, and making sure you're 100% confident in the spelling and what their specific names are. Because if I just wrote Cl- floating around, you would say chloride ion. But if you see a Cl inside of a coordination sphere, you know that it's chloro, right? Or Br- is bromo, or fluoro, or aqua, or amine, or ethylene diamine, and all these others, okay? Or cyano, and things like that, okay? So make sure you're very familiar with that, and the rest is really easy. So my opinion on these problems is you should never miss one. You should never miss one of these. You should get all the points for these, and then potentially miss maybe some of the others that are miss-worthy. But these are, it is your fault if you miss these. They are not designed to be difficult. They're just designed to test whether or not you listened and you knew what the process was for naming. Okay? So we have 3 of them up here, and it's probably not worth our time to sit and write them all out. But let's do, we can do probably this one and this one, because this one's a little different. And as you rewatch the video, or hurry and jot this down, you can try this one on your own, and there's tons of practice for these things, right? So first of all, we knew that this is our cation, so we're going to name it first, and then we're not going to put the cobalt as our first thing we're going to write here, but rather our ligands. We look at the 2 names for them. We have ethylene, diamine, and amine. We're going to order them in alphabetical order, so the amine comes first. Now, does it matter for my ordering these numbers down here and the prefixes that they'll receive? No. The prefixes do not matter, okay? So they do not factor in for how I place them in alphabetical order. Just the specific name of the ligand. So amine would come before the ethylene, diamine, A before E, so we're going to say amine, except there are 2, so we're going to indicate that by saying diamine. Okay, we've written that one out, so we now know that's in there. We're going to go to the second ligand. Now, we're going to do diethylene diamine. Okay? Good. Okay, I was waiting for like an uproar. Why don't we do diethylene diamine? Right, because in the name ethylene diamine, there is that prefix already that is just for the structure itself. So in order to distinguish that so that it doesn't sound like we have diethyl or diethylene, which is something totally different, and then diamine, so extra things as well, we know that it's just one piece, okay? So we say what then? Bis, ethylene. Notice I'm scribbling because I suck at spelling, so you can't see if it's right. Look how neat that is, and it just goes off. I do this on most of my assignments for my other classes, and that's really funny, not to like break the review and everything, but like recently, Taylor got in trouble in our other classes because he would like not know anything, but it's kind of one of those classes where they don't really read it anyway. So he would scribble all his answers, and he literally knew nothing. He would write things about chemistry in a physics class, like, so I'm a Chem 160A, but you could never read it. And they finally, like, on this last paper, what they say? They're like,
Taylor, slow down. It will bless your life.
Yeah, they're like, slow down. It's going to bless your life. It was so funny. So here's the thing. This is supposed to be all multiple choice. So is this type of thing going to screw you? No. But if he decides to be difficult, maybe he would have 2 where the spelling was a little off. So I'm pretty sure, my spelling stinks, but I'm pretty sure that diamine, amine in this case would have 2 N's, but the diamine in here only has 1, right? And so just be careful with things like that. Yeah.
Will ethylene diamine always have a bis or a tris?
Yes, it will always, because of the fact that in the name itself, it contains di. So we don't use the regular prefixes, okay? So grouping back together, let's finish this name. So we have diamine, bis, ethylene, diamine. And then what? Now I name the cobalt. So because it's a cation, I don't need to change its name, just cobalt. And then I'm going to throw in its charge. So putting in its charge, I just navigate. I know overall that inside of this sphere, it has to be positive because it is the cation. And so I look at what's in here of my ligands. Does any of these come with a charge to the table? No, they're all neutral. So nothing inside of the sphere is affecting the charge of the overall coordination sphere itself besides the metal ion in the middle. And I look at then what's on the outside. There are 3 Cls. Now, just a little tidbit of chemistry for the rest of your lives. How do you know the charge of Cl? It's always 1 minus. So just know this for the rest of your lives. The anions do not change their charges. So if you're doing oxidation reduction stuff next chapter and you see a Cl or you see an oxygen, the anions keep their charges. 2 minus for oxygen, 1 minus for Cl, okay? So those types of things don't change. But cations, they fluctuate, especially the metal transition, the transition metals, okay? So there are 3 of them, so 3 minus. So what was the charge of cobalt then? 3. Okay, it's pretty easy. we're able to do that. Now let's jump to this one, a little different. Oh, what's up?
If given a picture of the molecule, would we be expected to know like cis and trans and where to put that in the name?
I've never done one like that. Like if you just see the structure and know if they're cis and trans.
Yeah.
Do you know anything about
I
that?
think it'd have to be down the bottom. I don't think so. I don't think for a coordination sphere.
Yeah. I don't know where they would throw them together. I'm pretty sure if they wanted you to draw a specific isomer, they would tell you how it was because something like this could have different structure. It can be put together in several ways. And so he brings up a good point. This question is valid. Here's the thing. We don't want to talk about this very much because there's nothing I can say that's comforting or helpful. But probably the most difficult problem you will face on this exam is taking a coordination sphere and being asked to draw its isomers, right? That is difficult, and it's kind of what he's asking. How do you know, if I actually had to draw this out, how does all that go? That could be potentially the hardest problem you deal with on this exam, okay?
If you draw too many, will we get points?
Yeah, it has to be the right thing. You would miss, well, this isn't free response, so I don't know how it's going to work, and potentially it's impossible to do maybe with multiple choice, so you'd get off free for this. But all I know is in our meeting this morning, it was talked about that this is difficult to do. He asked us to do some. It's very hard. It's not easy. And so doing this, writing this out, and drawing the structure and the isomers, that's difficult. That is difficult. Okay, so there was nothing confirmed or talked about that's on the test, right? It was just he asked us to look at it because he also believes they're difficult problems. Okay? So moving away from that, now naming this one, we follow our rules. The first thing we notice is what we've written first is the K instead of the brackets. So we know our brackets is the anion and our potassium are the cations. Obviously, potassium stays as cation. Yeah? Yep. You are. Chloride. Yeah. Thank you. Okay, so finishing this.
It's
Not yet.
Chloride. It's always chloride, right?
Just chloride.
Yeah.
Yep. Just like any ionic naming, you don't do mono and stuff like that for ionic naming. And once you've got outside the brackets, you're looking at an ion now. Okay, so we're gonna write potassium. Okay. Next, we're gonna do naming the sphere. Naming what's in the brackets never changes. So we do not write the middle metal ion, but rather we write what the ligands are. And we have ammonia, chlorine, and bromine. So we have amine, chloro, and bromo. Okay, so A, B, and C should be pretty easy to put together. So we're going to have diamine, dibromo, dichloro. Now what? Now the fact that it is an anion, I change the name of the middle metal, right? Instead of saying copper, I would say cuprate. So again, there are some names you got to be familiar with and have memorized. And these are all in the charts in the slides. So now it would go cuprate. Do I need to put the charge?
Yes.
Absolutely. So what is the charge? 2. Good. Okay. So this is naming. These are the two types of examples you could get. Okay. Having the coordination sphere as the cation or having it as the anion. Now, there was a lot of frustration with the recitation quiz, with spelling and things like that. And I know, because in my sections too, people were missing it, and it technically was correct, but they just put a space between the charge and the rest of the name. But that's just learning speak. But you should, again, these are problems you shouldn't miss. Just take your time, take it slow, and know that it follows the same pattern. Yeah? Sure. Yeah, and you just follow it the exact same way. Okay, so I wrote this up here, chelating effect, just to remind me to talk about something that I noticed in the slides, a potential dagger, I guess, bleeding some points out on the test. Chelating effect, who knows what that is? The chelating effect was talked about briefly. What this is, what chelating effect is, first of all, what is chelating agent? Well, it's a lot like a ligand. A chelating agent is something that is polydentate, which means it binds to a ligand or binds to a metal atom in 2 or more places, right? That's important. It's not just any ligand. It's not amine or it's not like water, but bonds in 2 or more places. And it goes and gets maybe something that's harmful to our bodies or some substance that we don't want in some solution or anything. It's just unwanted. And we put a chelating agent in, and it's able to go with its lone pairs and in several areas, if not lots of areas, bind to that center piece. So EDTA is one we've looked at. It binds in 6 places, right? So basically what it does is if this is the little metal atom we don't like, this structure will come in and engulf this metal atom by bonding, just like coordination sphere chemistry, right? It bonds all over it, so I'm just going to kind of go like this. It bonds all over it, and then what your body or whatever the solution is exposed to is no longer the metal, but what's on the outside of the chelating agent, which is usually carbons, oxygens, nitrogens, and hydrogens, things that aren't harmful to us, okay? So that's what a chelating agent does. The chelating effect is the fact that when you do that, you go from something that is all by itself, so its entropy is pretty low, to all of a sudden bonding this really complicated molecule or compound onto it, this chelating agent, and then as a whole, when they group together, the entropy of this system versus when it was by itself goes up, right? And that drives the reaction. So that is almost a one-liner. It's maybe good to have in your back pocket. Chelating agents, when they bind, it makes the entropy go up, and that is the force that drives the reaction to keep occurring, okay? So that's something good. I had just thought of something else that was really valid to talk about, but maybe with these questions I'll remember. Yeah?
What reaction does it drive?
It drives the reaction of the chelating agent binding and going. Yeah, so it occurs a lot, right?
Could any polydentate ligand be considered a chelating
Sure.
agent?
Any polydentate. If you look on the side, it says a chelating agent, a ligand or polydentate ligand that bonds in 2 or more places. Yeah, could be some compound like that. This is what I needed to say. Understand the nature of a coordination sphere bond. So that covers everything we've looked at on this board. Chelating agent bonds, the bonds within the coordination spheres, right? They aren't ionic bonds. They act like covalent bonds, okay? They act like covalent bonds, all right? So the nature of coordination sphere chemistry bonds is covalent in nature, okay? Not as ionic. Now the bonds between the brackets and what's outside, now that's ionic. But inside is more covalent in nature, okay?
The act of one polydentate bonding with a transition metal more than another, is that also called chelation? Or you see what I'm saying?
Chelation is this process.
Okay, it's that process of like
Yep.
a replacement of the. Sorry, I'm trying to.
I know exactly what you're trying to say. It's yes. Chelation,
Polydentate.
yes. Replacing it and getting polydentate ligands to bond something, that is chelation. Yep, exactly. Okay, so Corbin, will you just blast the thing up? We're going to blow through this next stuff. All right, so everybody's nemesis is isomers, right? Everybody in the tutorial lab's been losing their minds about isomers, okay? Stereoisomers, structural isomers, enantiomers, chirality, and things like that. We're just going to clear that up so it's really clear, so you know what you're getting yourself into, and it's not that bad, okay? So isomers is something we dealt with in Chem 105, so I'm going to speed through the definitions of that. It is any compound that has the same chemical formula, but it's put together differently. And there are lots of ways to put something together differently, down to clearly being put together differently, where you look at 2 molecules and you say, just by looking at them, they look completely different. One is in a ring, one is spider-webbed out, but if you wrote just their formula, they're the same, right? That's what an isomer is. And when it's clearly different like that, it's usually a structural isomer. Structurally, it's different. But when this difference is slight, or comes down to the orientation around a stereocenter, right, or a chiral carbon, or some specific point on the molecule, that is a stereocenter. Those are more difficult to see, and we are dealing with both. So the structural isomers, which are easier, that we're dealing with in this class, all have to deal with coordination chemistry, right? And what a structural isomer is, there are two types we care about. So structural isomers like the mother term, and here are the subterms here. Linkage or coordination sphere isomers. A linkage isomer, if you look at the examples I've drawn here, the only difference between this one and this one is if you look at the NO2 group that's bonded, this one is bonding directly to the nitrogen, and this is bonding to the oxygen. But if you were to just write the formula, it's just NO2, right? And so unless you saw it written out or drawn out like this, you wouldn't know a difference between the two. But this is what a linkage isomer is. It is different. Chemically, it would react different and do different things. But it's not a huge difference, but it's easy to see. Okay, that is linkage. Linkage is this. Okay, coordination sphere. Coordination sphere is, remember when we have the brackets, that's the sphere, and what's outside the brackets are just random ions that are kind of being attracted to the positive or negative sphere. This isomerism, all it does is if you look at this one, this is what would have been in the brackets, and these Br minuses maybe what would have been what was outside of the brackets. But then when we switch over here, this one stole a place of the chlorine and jumped in, and the chlorine got kicked out, right? So this is coordination sphere isomers, where what was inside the brackets in the formula, we took something from outside the bracket and switched it with something from within the bracket and booted that thing out. So they switch places. So you don't actually have to see the structure drawn for this. You could just see the formula and notice that in one to another, they just kicked something from the inside out to the outside and pulled something in. That's a coordination sphere isomer, and that one sort of is self-explanatory. The coordination sphere is changing its structure, okay? So it boots it in and out.
So for a question on the coordination sphere, he'd have to give us two different molecules, right?
Yes. So he brings up a good point. With isomers, you have to always compare two things together. You can't just look at one by itself and say, oh, that's a coordination sphere isomer. You could say it probably has one somewhere, but until I can see one and compare it, then that's the only time you can talk about isomers. So if I tried to compare this with this, there's nothing to compare. They're completely different things, right? So I can't look at this and say it's an isomer of that, or if I didn't see this one, I can't just say this is an isomer. It probably has an isomer, but until I get something on the board next to it, that's the comparison made to say what type of isomers are they to one another and things like that, okay? So those two should be pretty straightforward for you. The next ones are a little harder. Thank you. The next ones are a little harder. Structural isomers, clearly easy to see, very clear difference. The next type of isomer, right, which is the other mother term, is a stereoisomer, which is when the only thing that changes between the two compounds is a very specific region on the compound itself, just the orientation of how they are. So there are two types of stereoisomers. There are enantiomers, which we care about right now, and then there are diastereomers, which are the other guys, and we haven't talked about them, and we're not going to jump into them. But the reason I even wrote it is because if you are an enantiomer, you are a stereoisomer. If you are a stereoisomer, you're one of these two, but you don't have to be an enantiomer, right? It's like saying you're a human being, you're a boy or a girl, right? You're one of the two, hopefully, but you don't have to worry about this one, okay? All right. So if we look at these now, this looks silly on the board. It looks silly, but I'm going to start basic, and then you guys be on your own for all the hard ones. No, they do get harder, but this is basic. Let's start here. So if you look at this arrangement here, if I try to compare these two, there's no type of structural difference. I don't have new things coming in from the outside. I didn't draw specific compounds that weren't just shapes, right? Where you say, oh, this is bonded to the corner and not the flat edge. Nothing like that here going on. But I just have shapes because with stereoisomer, it doesn't necessarily matter what's bonded there, but where it's located amongst the other bonds. So let's look at these two. I have my triangle, my square, my circle, and my star, right? Now, I'm trying to say, are these stereoisomers of one another? Let's compare this one with this one. Well, it's not something you flat look and go yes or no. Like a structural isomer, you actually have to manipulate this in your mind a little bit, which is something that I can't teach you. It's something that we can't go over and have it be like, that clicked for me. It's something you're either really good at it or you struggle a little and have to practice or buy models. But I'm going to try to talk this one through And hopefully you can see maybe something that I like to do for some of this isomerism problems. So if I want to know if these two are the same, or if there's a stereoisomer, the first thing I do is I just orient myself among one of them. And so if I was holding this by the triangle, right, and I'm looking at this piece, right, the circle here, if I am the circle, to the left of the circle is a square, right, to the right is the star. So if I am the circle, left is the square, right is the star. Okay. Because they look pretty similar when you just draw them up here. So if I go back over to here and I hold it from the top, and I become the circle again, to the right is the square now instead of the star, and to the left is the star. So these two, they are not the same compound. They are absolutely different. And you would think, oh, can you just keep rotating it around? No matter how much you rotate it, this one has the star to the right. Anywhere you rotate that circle around, the star is just on the right of the circle. But over here, right, it's on the left. So these two are mirror images of one another, right? So they're mirror images, but this will not stack on top of this, right? They are different. I cannot get them to line up perfectly. They'll always have those two in different spots. So when that type of situation occurs, these are enantiomers of one another. Again, stereoisomers or any type of isomer, you have to have two things to compare to. If all I did was draw this, I can't call this an enantiomer. But if I have something to compare it to, I can say these are enantiomers of one another. So where this gets confusing is in the slides, he says, all enantiomers are chiral. That's absolutely true. We're going to get into chirality really soon. That's true. But not everything that is chiral is an enantiomer, and those two aren't how you solve either one of those problems. You don't look for chirality to solve enantiomerism, or look at enantiomerism to solve chirality, right? You don't look at one to solve the other. Rather, you look at each one separately, but know that if you are an enantiomer, you're also chiral, so that's a given, okay? So if we were to try to compare these two, to make it quick, I'll let you know, they're the same. All I did was this one, if I rotated this one down, it becomes this one right here, okay? So those two are the same. Now, the ones you'll deal with, this is a tetrahedral, you'll probably deal with octahedral situation, or chemistry of stereoisomers that look like that. They are more difficult to see, but it wouldn't do us any good to spend 5 minutes getting freaked out over looking at something that I can't even explain in words, versus talking about something that I can easily do right and left and you can see why they're different, and then trying to take some of that idea and jump to that, okay? So the last thing to tie in with chirality, what it means is something that is optically active or bends light. Light comes in, and when light comes out, it's bent in a different, it rotates the light in a different direction. So we know that there's a wave-particle duality of light. Really quick, if light's traveling, we can have it going up and down, or side to side, or at an angle. And if it's up and down, it comes into a molecule, and by the time it gets out, it's going side to side. So it rotated the light. Something that does that is chiral. Molecules that do that do not have a plane of symmetry. That is all you're looking at. If I can draw a molecule and you can find a line to cut the molecule in half and get two equal sides, it will not bend the light and is not chiral. But if you cannot find that line of symmetry, no matter what you have, it will bend the light and it is chiral. So notice, chirality, you do not need a partner. You do not need to draw a mirror image and see if they stack to see if something is chiral. If you want to do that, you're looking to see if they're enantiomers, and if they are, then they're all chiral. But you can predict if something is chiral by just looking at it by itself. That's the point. Just try to find a line that you can draw and get two equal halves. If you do that, right, you get two equal halves, it will not bend the light, it is not chiral. So you go through every problem in that manner. It's pretty simple. You can just try to draw a line. If it gets confusing, that is a bulletproof formula. Draw the line. And a quick thing, just a little quick thing. If this is a molecule right here, and if I could draw a line right down the middle, which I can, some people would say, well, the hydrogen, though, it's on the right. Little pieces like this don't affect whether or not this is chiral, right? The main molecule itself, I could split this into two halves, cutting the OH group in half, right? So just because of where you drew the hydrogen coming off does not affect chirality. You're not going to get a problem that looks like this. This is an organic molecule. But if you get like NO2 and then one over here and they just look like they're a little different, how they're shaped, not valid, right? That's not important. Okay?
A lot of people talk about chirality with 4 different groups to the carbon.
That's
Is that-
stereochemistry.
Okay.
So you get a stereocenter if you have a carbon bonded to 4 different things, right? That would form a stereocenter. But chirality is literally just planes of symmetry within the molecule. And here's the point being, if you don't have a plane of symmetry in the molecule, you will have stereocenters, which are what ultimately rotate the light. But doing that many steps to solve a problem like this is tedious and unnecessary, and it gives you more stumbling blocks. But just looking for a place to draw a line, that's what's going to get you through, chirality or not. So sometimes he doesn't actually draw them out like stick hand like this. He actually shows a picture of maybe a model put together. It's hard to see, but if you could find a place in that model structure to split it in half and get 2 slices and they're equal, not chiral, okay? Sweet. You want to take that question? Yeah.
I was just gonna point out, there was a smart word problem that had 2 chlorines, and so it looked like didn't have 4 different, groups bonded to it. But I asked Dr. Macedonia about that, and the problem was that was octahedral, so the 4 different groups only applies to tetrahedral molecules.
Correct. Yep. Octahedrals have different rules. Okay, so switching gears, we're going to start talking about the light, crystal field splitting theory, and all that fun stuff, okay? So just to review quickly, you went over this in Chem 105, so I'm going to go quickly. If it's been a while, this will be as good enough as a review that you need, okay? So when we look at the light, we're looking at the visible light spectrum here, okay? Now, there's just a mnemonic that you just need to memorize, Roy G. Biv, okay? You've probably heard that in Chem 105. So this is red, orange, yellow, green, blue, violet, all right? And this is an increasing energy, okay? So red is going to have the least energy associated with it, and violet's going to have the most energy, okay? So which side has the lowest wavelength? The left side. As I increase in energy, I'm decreasing in wavelength, okay? So lower energy light has longer wavelengths, higher energy light has shorter wavelengths. Okay, so this is something you absolutely just need to know and memorize and write it on a scratch paper. Just brain dump it right when you sit down with your test. Just draw the color wheel, okay? That's what I did. This is going to help you answer a lot of questions, okay? So just in the same exact order, just start somewhere. Roy G. Biv, and just go around the circle, okay? So let's talk a little bit about absorbance and how colors show, okay? So my shirt is red, okay? Crimson to be specific. So what color is my shirt absorbing? It's absorbing green. Good. So my shirt is absorbing green, and this is why the color was important, because whatever the thing absorbs, it's going to look the exact opposite of the color wheel. And what this red is, it's the sum of all the remaining colors. So basically my shirt is taking in all the green light, and everything else is reflected. And the sum of all those different lights reflected equals red. So that's why I see red. So looking at this is an absorbance spectrum. You've probably seen something like this before, okay? This is absorbance, and this is wavelengths down here. Now one thing you might just want to be familiar with that might help you out, the visible light spectrum is 400 nanometers to 700 nanometers, okay? So 400 nanometers is the shortest wavelengths, so those are going to be like the violets. 700 nanometers is the longest wavelength, so that's going to be like the reds, okay? So looking at this absorbance right here, what color is this compound? Okay, who can explain it? Like, who thinks they just know it? Yeah.
So it's absorbing more into the violet and the blue range.
Okay.
So you're going to be looking more towards your orange and your yellows.
Awesome.
What color it's going to show.
Awesome. So looking at absorbance, it's absorbing higher energy light, lower wavelength light. This is in the 400 range, 400 to 500 range. So this thing is going to be absorbing these high energy lights over here. So it's going to look to us exactly opposite in the color wheel. So it's going to look yellow or orange. Yes?
Is he going to give us the color spectrum on the test?
No. Yep, that's why you have to draw this. Yeah. Just know 400 to 700. You don't have to memorize like red is 700 to 650. You don't have to memorize those exact values. It's going to be more of relative things, colors relative to each other. So if you just know that red is the longest wavelength, violet's the shortest, you're going to be fine. Okay, any questions on this right here, this absorbance spectrum? Yeah.
I've noticed sometimes he'll switch the y-axis to intensity, so the thing that is not absorbed, but rather what was seen on the other side. So just watch the y-axis. This is absolutely correct with absorbance. And I've just seen one that said intensity of what was not being absorbed.
Yeah, or transmittance.
Yes. So just look at that. Just make sure it's not always that exact way.
Not always absorbance. If this was transmittance, then the blue and violets would be getting through,
And it's absorbed.
so they would be showing purple.
Right.
So watch that y-axis. Thanks, Bray. Any other questions on this? Okay, let's move on. You have a question? Yeah.
So if that graph looked exactly like that, and the y-axis was transmitted, what would the answer be?
It would be violet. Because if this is transmittance, then the most transmittance is happening in the blue-violet range. And transmittance means that color of light's getting through. So it would look purple to us. Okay, so let's move on to the spectrochemical series, okay? Now, this is something that I was told you don't have to memorize. So you don't have to, I think he's going to give you this, but he's probably not going to write down what I'm going to write on the board now. So you can expect this on your test, but don't expect anything else that I'm going to write down. So these things you have to memorize. This is another thing that I call brain dump, okay? You get in the test, you just write that on your paper so you know it's there. You don't even have to think about it, you just know it's there. When it comes up, you can refer to it, okay? So these that we're talking about right here, these are our ligands, okay? So when we talk about Lewis bases and Lewis acids, are these the Lewis bases or are these the Lewis acids? Bases. They're the bases, good. So these are the electron paired donors. They're the things that are going to come on and attach to the metal ion, okay? So when we look at these, one thing you just have to memorize is that these down here on the left are weak field ligands. And these over here on the right are strong field. Now there's no exact like dividing point where we say, okay, H2O is strong and fluoride is weak. There's no like direct line. What you're gonna have to know is it's relative. It's a spectrum. So he's not gonna make you do something that's like dead center in the middle and ask you whether it's gonna be like a strong field or a weak field ligand. It's gonna be on further to one side. And we have some examples about that as well. So what this tells us, this weak field and strong field ligands, is it tells us how the crystal field splitting is going to happen, okay? So just something that you guys understand, transition metals have 5d orbitals. They all have 5d orbitals. So if we were looking at something like cobalt 3+, cobalt 3+ has 6 valence electrons, okay? So if I were to just draw it out, cobalt 3+ by itself, it would look like that. 6 valence electrons, okay? What happens though is that when one of these ligands comes in and wants to attach to that, there's some repulsion. Okay, that ligand is an electron paired donor, and I already have these d electrons that this metal ion has. So there's going to be some natural repulsion there. And because of that repulsion, we see this splitting, this crystal field splitting, and that's where we have to draw these diagrams. And there's different ways they can split, and I'm going to talk about that later. Okay? But for now, we're just going to go with octahedrals. So these are our Ds are all the same energy level. When the ligands come to attach, that's when the repulsion happens, and they have to split into those different energy levels. And when that happens, that's when it's important to know how they're going to fill in those orbitals. Okay? So, looking at these weak field and strong field ligands, what this tells us is how big the energy gap between those orbital levels are. So if we have octahedrals, if I have weak field ligands, this is going to be a really small energy gap right here. The symbol they usually use is this delta symbol. It just means the energy gap right here, okay? Now as I'm increasing the strength of my ligand, this gap, that wasn't that much bigger, gets bigger and bigger, okay? And then when we get to the strong field, the gap's even bigger. So as I increase the strength of my ligand, this energy gap gets bigger and bigger. So now let's talk about how light is absorbed. Light is absorbed when one of these d electrons down here that's sitting in this bottom level, an unpaired d electron, gets promoted to the higher level. That's when light's absorbed. So because each of these ligands attach and make different energy levels, each of these things is going to absorb a different energy or different wavelength of light. Okay? So stronger field ligands are going to make a bigger energy gap, therefore they're going to absorb higher energy light. So if they're absorbing higher energy light, what color are they most likely to show? Yellows. Yellows, right? Use the color wheel. Don't forget about the color wheel. If they're absorbing the highest energy light, they're absorbing violet, so they're going to look yellow to us. So basically, we have all different colors of light that are coming in and hitting this thing. But the light energy has to match that energy gap perfectly to get that electron to jump. So for example, if I have all the colors coming at this, the red's going to pass, or the blue's going to pass through, the violet's going to pass through, the orange is going to pass through. But since this gap is so small, the red light's energy matches it perfectly, and that's what moves the electron up. So the red light would be absorbed, because it's a small gap, and it would look green to us. Okay, any questions on that? This is just the strength of ligands. So as you increase the strength of ligands, you increase the energy gap, and the light that's absorbed has to match that energy gap perfectly. Do you have a question?
Yeah, so I'm just thinking about application here. Does that mean that a chlorine ring would be a weak field ligand?
A chlorine ring?
Chlorine, like in chlorophyll? Because that's a polydentate, and they
Yeah.
have high affinity, right?
Mm-hmm.
So
Probably be a weak field ligand if it's chlorides, yep. Yeah.
So is that why like things with a lot of energy are like yellow, like electricity, or like if you get shocked, you know, like?
That's a really good question. I don't think so, because this is all coordination spheres. So these are like colors in solutions. Like remember when he brought out all those colors? It's a really cool idea though.
I have a question for you. Get so scared that you.
Yeah.
So that splitting energy is directly related to the wavelength of light.
Correct. Yep. So high energy gap, this is going to absorb low wavelength light. Okay? Okay, there's one more thing we can talk about here with this series. Okay? Weak field ligands have high spin electrons. So weak field ligands have high spin electrons, and low field ligands, or strong field ligands, have low spin electrons. Now this is super important, and this is what changes the way that we fill in our diagrams. Okay? And I have an example problem on this as well. But basically, the way you want to think about this spin, it's the spin pairing energy. So electrons will always take the path of least resistance. When we're going to fill in electrons here, let's say we have 4d electrons. I need to fill in 4 electrons. There's 2 ways it can happen. It can either go 1, 2, 3, 4, or it could go 1, 2, 3, 4. Okay? So what we're comparing here is the energy for an electron to get up to this next level, or we're comparing the energy for this last 4th electron to flip its spin and get paired up. Now, if electrons are high spin, that means they have a high spin pairing energy, and that pairing energy is going to be greater than the energy of just going up to the next level. So high spin electrons from these ligands will form this. They would rather just take this hike up to the next level than flip their spin and get paired up. Low spin electrons from strong field ligands, this energy gap is so big, they really don't want to hike all the way up there, and they have low spin pairing energy, so it's much easier for them just to flip their spin and get paired up. Okay? Any questions on that? That's basically all you have to know right there, is that high spins will go up, low spins will pair up. Okay, so here's this next problem. For the sake of time, we can't just like give you guys a couple minutes to think through it, but just look at it real quick. This should be a quick one to identify. The question is, of these compounds right here, which is blue, which is yellow, and which is purple, okay? I'm not talking about absorbance here. I'm talking about the color that my eyes see, okay? So immediately, the first thing I can do is let's just rank the strength of the ligands. Right? So looking at my spectrum up here, I have Cl, H2O, and ethylene diamine. Okay? Cl is the lowest strength ligand. So this is low, this is middle, and this is the strongest ligand. Now, as soon as I've identified that, I know that strong field ligands produce bigger energy gaps, so they're going to absorb higher energy light. Okay? So what color is this one most likely to absorb? Purple, violet. Okay, so what color is it going to show? Yellow. Yellow, okay. How about this very low one? What color is this going to absorb? Yellow. Like reds, yep. So what color is it going to show? Green, okay. How about this middle one? Did you notice how I did the extremes first? If you jump right to the middle one, it's kind of hard. But I'm going to do the highest one and the lowest one, and then the last one has to be it. So this middle one, we're saying it has to be blue because that's our only option, so it would be absorbing orange. Okay? So the color wheel is your best friend. Purple is the low one. The low one. Yep. Okay. So this is something, yes?
What absorbs the lowest intensity light? And orange is lower intensity than yellow, so it should be blue, right? And then the middle one should be purple.
Did I say it wrong?
Yeah.
Okay, sorry, yeah, I said it wrong. So this one is the low, so this is going to absorb the lowest energy light, so it's going to absorb like reds. So this one should be green. Is that what I said? Or did I say the opposite?
It should be
Green's just not.
Oh, green's not up there. Okay. Okay, yeah, blue. Sorry about that. Yeah. That's why, like, you can never just tell by looking at it. It has to be like what your options are or just comparing relative to each other. Okay. So this is something that's going to be really quick right here. When these ligands come in and attach, there's different ways they can do it, okay? What you've seen is octahedrals, tetrahedrals, and square planar, all right? So octahedral, this is something you just have to memorize, is 3 on the bottom, 2 on the top, okay? So this is an octahedral. 2 on the bottom, 3 on the top is tetrahedral. Now, one thing to note about tetrahedral, they're always high spin. That's something that's just on the slides. Always high spin. Just note that. And this very last one is square planar. And square planars are typically low spin. This is all on the slides. So if you're like struggling to write it all down, you're fine. It's all on the slides. So these are typically low spin square planars. So when they give you splitting diagrams for a tetrahedral, treat it as high spin. It doesn't matter what the ligand is, tetrahedrals are high spin. Okay, here's another problem for you. which splitting diagram for each of these coordination spheres is incorrect? Okay, you can take a minute to look at this. Find out which one is incorrect. Make sure the video can see it. Yeah. Okay, let's talk about it. Let's talk about it, okay? The first thing I'm looking at here is what kind of splitting I have. What's my structure? What's my sphere? Okay? So if you would memorize these, you would know these are not three octahedrals. This is an octahedral, a tetrahedral, and an octahedral. Okay? So let's go through this one on the right first and see if this is valid. Okay? 3 ethylene diamines. So cobalt 3+, when you do it, it has 6 d electrons. So I have to fill in 6 places. Ethylene diamine. Am I going to say this is a strong field or a weak field ligand? Strong field, which means it's high spin or low spin? Low spin. Low spin pairing energy, they get paired up. So this is correct. They get paired up before they go up to the next level. Okay? So this one's correct. Let's do this one. Okay? It's a tetrahedral. So chlorine, are we going to say this is a strong field or weak field ligand? Weak field, which means normally it's what? High spin or low spin? High spin, right? So this one is what? This one is in. Okay. Okay, I messed it up. There's 2 that are incorrect. I made this up like a minute before the review, okay? What I was trying to do, for some reason when I made this, I was thinking that tetrahedrals were low spin, and I was trying to show you that it doesn't matter. I should have used a high field or a strong ligand here to trip you up better. But I'm just trying to show you that because this is a tetrahedral, it doesn't matter what the ligand is. It's always high spin. So that's just something you have to memorize. Tetrahedrals are high spin. Doesn't matter what the ligand is. Yeah.
So how do you know if it's a tetrahedral or an octahedral?
Just by the way this is. So an octahedral is always 3 on the bottom and 2 on the top. A tetrahedral is always 2 on the bottom and 3 on the top.
But how do you know which way it should be? So how do you know, like?
Oh, I knew this was tetrahedral because I only have 4 things attached. If my coordination number is 4, then it has to be a tetrahedral. The reason this is all messed up is because I originally had cobalt here, but cobalt 3+ has to have a coordination number of 6. And so last minute I came and changed it to platinum, and I didn't change the number of electrons. So those are wrong too, but I had just caught myself that I made a mistake, but I didn't fix it all the way. Yeah.
Why does it only have 6 electrons?
I'm saying it's wrong. So I originally had cobalt Cl4 here, but cobalt 3+, like Braden said, is one that you have to memorize. Its coordination number is always 6. So cobalt Cl4 cannot exist. There would have to be 6 Cls there. So I came and changed it last minute to platinum, but I didn't change the electrons down here, so those are wrong. Yeah.
Okay, so you explained how we know that the middle one is tetrahedral. What about the other 2? Like, how do we know that it's octahedral?
Because it's 3 on the bottom and 2 on the top. That's it.
Oh, so they only try to trick us.
No.
They usually give you the graph.
Yeah, they'll usually give you the orbitals. But if they just gave you the molecule and you knew that there was 4 things attached, then it has to be a tetrahedral. If there's 6 things attached, it has to be octahedral.
Can you explain why cobalt can't have
four chlorines.
It's just a memorized thing. It always has a coordination number of 6. And platinum always has a coordination number of 4. And these are 3. So cobalt 3+, chromium 3+ are always 6. And platinum 2+ is always 4. You just have to memorize it.
They never change for any of the
They never change. They're always that. Yes?
So how do you tell between tetrahedral and square planar?
You wouldn't be able to. Yeah, they'd have to show you a picture of it. Yep. Okay. So last thing. Yes?
How do you know how many electrons are on the
So you look at the ion. So in this case, platinum, this should be a platinum 2+. So what you do is you jump over to the periodic table and find PT. It's number 78. And you have to find what the electron configuration of platinum normally is. So in this case, it would be 6s2 for its valence and 5d8. So if it loses 2 electrons, it's going to lose both of its s's, and it's still going to have 8 in its d. So this should have 8. So it should have 2, 4, 6, 7, 8. Wait.
2 more. Right there.
Yep.
the platinum or the cobalt?
Yeah, because the metals are the only ones that have d electrons. All the ligands, they don't have d electrons. So it's always the ion that determines how many. Good question. Okay, last thing. Magnetism. This should be really quickly. This is all in the slides as well. It's really clear in the slides. So there's 3 types of magnetism you need to know. Ferromagnetism, paramagnetism, and diamagnetism. Okay? This one right here, where all the electron or the magnetic moments align, this is ferromagnetism. So when I introduce a magnetic field to something that's ferromagnetic, all of the electrons will align with that metal field, or with that magnetic field. So what you need to know here is that neighbors influence neighbors, okay? The fact that some of these are turning forces all the other ones to turn. Ferromagnetism. This one is paramagnetism. If I introduce a magnetic field to something that's paramagnetic, some of the unpaired electrons are going to line up, okay? But what you need to know about this, so there will be an attraction if there's something that's paramagnetic, because some of the magnetic moments are aligned. But what you need to know here is that neighbors do not influence neighbors. So the fact that one turned towards the magnetic field doesn't make the rest turn like in ferromagnetism. And if there's no arrow in it, that means these are paired electrons. So these are orbitals I'm talking about. If there's nothing in it, then there's 2 electrons in that orbital, and therefore it's diamagnetic. There's no attraction. Okay, the very last one is diamagnetism. And this is when every electron's paired. So if I had a diagram and every single one of these was paired, this thing would be diamagnetic. Okay? Not going to do anything. It's going to be repelled. No attractive force. It's just going to be repelled from the magnet. And that's magnetism. So, watch the video again. And, yes, good luck.
Which one had to do with electric current?
With what?
Was there something about running an electric